chemistry class. You guys can see I'm in my kitchen and I'm recording a video on the basics of thermodynamics or thermal chemistry. There was that day I was gone before all of this chaos happened, so I know that we talked about some of this, but not all of it. I wasn't quite sure how far we got, who was there, who wasn't there, so I'm basically just going to start over. These notes should be on Google Classroom, so if I go too fast for you to write it down, you can always pause, or of course you can always go back and look at them. But we're going to continue on talking about thermochemistry. We'll do nuclear chemistry coming up, and we're going to try and just end out our year as normal as possible. So, starting with thermochemistry, we want to be able to distinguish between systems and surroundings. A system is going to be the part of the universe that you are really focusing on, or where all of your attention is gathered to. So that would be like reactants and products, or the stuff inside of a beaker. And then the surrounding is going to be everything else. So all the other stuff, the beaker itself, the atmosphere, whether or not there's a hot plate, that kind of stuff is all the surroundings. So the surroundings and the system can interact by transferring energy, which we'll get to later, but you're really only paying attention to what's going on with the system itself. So again, in a chemical reaction, that includes the reactants and products. You also need to describe the state of that system. So a state of a system will consist of its composition, or what it's made up of, as well as the temperature and pressure of that system. So you should be familiar with standard temperature and pressure, or STP, which is room temperature, so roughly about 25 degrees, 1 atmosphere of pressure. And then for our example here, we have 50 grams of hydrochloric acid at 50 degrees Celsius and 1 atm, or 1 atmosphere of pressure. So all of that is what's involved in describing the system and the part of the universe we're focusing on. When we're talking about heat flow, we're talking about this property called Q. So Q is heat flow. If you are adding Q, or heat, to a system, then it's going to be positive. So because it's coming in, you are increasing the heat within that system, therefore making it positive. This usually involves an increase in temperature. However, if it's leaving, then Q is going to be negative, because now heat is going from the system outside, so it usually decreases the temperature, thus making a negative Q. When you're talking about reactants and products, we can get two different types of reactions that occur. Endothermic is when Q is greater than 0, or positive, because this involves heat flow into the system from the surroundings. So our example here is that you have an ice cube, so solid water, that's going to melt, which is liquid water. In order to do that, the solid water, or the ice cube, has to absorb heat from the surroundings to become a liquid state. So the temperature of the surroundings can drop a little bit because it has to give heat to that system. Exothermic reactions are the opposite of endothermic reactions. So in this case, Q is going to be negative, and it'll involve heat flow from the system to the surroundings. So heat has to leave the reactants and products and enter the rest of the universe, and it will increase the temperature of the surroundings. So the example for that is like combusting methane, which is what we do when we light our Bunsen burners. The equations down there, you can see CH4 plus the oxygen in the atmosphere is going to burn, creating carbon dioxide and water. And that is an exothermic reaction because it is releasing energy into whatever it is that is surrounding it. Q is typically expressed in joules or kilojoules. So it's named for James Joule, who is a guy that carried out some very precise measurements and established the first law of thermodynamics, which we will be coming up to probably not this lecture or the next one, but the one after that. So in the past, chemists used to use what we call the calorie, which should sound pretty familiar because we have probably all counted calories before, or at least paid attention to what those calories are. But what you're actually consuming is really a kilocalorie, so 1,000 times bigger than a calorie. The amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius is 1 calorie. So 1 gram of water going up 1 degree Celsius equals 1 calorie. that's an energy unit. 1 calorie is going to be the same as 4.184 joules, and 1 kilocalorie is the same as 4.184 kilojoules. So remember, because this is a metric system, you're working in denominations of like 10, so we're talking 1,000 times bigger when we're going from calorie to kilocalorie or joule to kilojoule. The relationship between the magnitude of heat flow and temperature is expressed by Q equals C delta T. Delta just represents the change from the initial state to the final state. So if you're going to get the delta of anything, you take the final minus initial to figure out that change. So in this case, if we're talking about delta T, we're going to take the temperature final minus the initial temperature, and that'll get us the change in the temperature. We multiply it by C, which is known as the heat capacity of a system, to get Q, which again is our heat flow. So the heat capacity represents the amount of heat required to raise the temperature of the system 1 degree Celsius. So in this case, it's not specific to water, it's just the temperature of that system itself. For something that has mass, which is going to be largely what we are dealing with, you're going to take the mass times the C times delta T. So you'll get the expression Q equals mc delta T. C is known as the specific heat, so notice the difference between our two C's is one was capitalized, this one's lowercase. Lowercase is the one we're going to work with most often. This equation is the one we're going to work with most often because most of our stuff has mass, unless we're talking about gases, which have their own crazy stuff, which we learned about before. So lowercase c, or specific heat, is the amount of heat required to raise is the amount of heat required to raise the temperature of 1 gram of that substance 1 degree Celsius. It's a physical property, just like boiling point or melting point or density, and it can be used to identify the substance or how pure a substance is based on what that specific heat is. There's a big list out there already of all these specific heats of different substances, and the same substance will have different specific heats based on its state of matter. So steam versus liquid water will have very different specific heats. Because this data is already out there for you to use, I will either give it to you in problem or you'll have a table in which you can refer to look it up. So this is our first knowledge check, and it's going to also be the ending of this first lecture. What I want you to do is try and use that equation and the information that's given to solve our problem. So we're going to have two problems. We need to compare the amount of heat given off by 1.40 moles of liquid water when it cools from 100 degrees Celsius to 10 degrees Celsius. And then you want to compare the same amount of steam cooling from 200 to 110 degrees Celsius. So the C for liquid water, or the specific heat for liquid water, is 4.18 joules per gram degree C. And the specific heat for steam is 1.87 joules per gram degree C. So why don't you guys try this on your own, post your comments below, or not below I should say, in our Google Classroom. And I'll check back again tomorrow.